Hi, everyone. Um, Today, I am very happy to introduce Professor Ke Fang. Ke is a professor at University of Wisconsin, Madison, and she is an expert on high-energy particles in the universe and neutrinos. So some has been some very exciting research recently, which she was involved in, even led by IceCube, for example. Before going to Wisconsin, Kerr was an Einstein Fellow at Stanford and a JSI Fellow at Maryland and NASA Goddard. And before that, she received her PhD at University of Chicago in 2015. And Kerr is also an investigator in the Simons collaboration on extreme electrodynamics of compact sources. Yeah, Kerr, thanks so much for still giving your talk despite that you couldn't come in person, which you found out last minute. So yeah, thanks a lot for that. And yeah, show us your amazing work.
Thank you so much for the introduction, Bart, and hi all. Sorry about the last minute change from in person to remote. I have a 1-year-old, and the uncertainty associated with this age is larger than the systematics of any astronomical detector I ever know. So here I am going to tell you remotely about the efforts we have made in the hunt for the highest energy particle accelerators. So as a start, I'm bringing up the wiki page as a transition. This is what we have known from the electromagnetic waves, and this is what traditionally has been used to probe the universe. And for junior students in the room, this is what showing you the broadband spectrum of a electromagnetic radiation. And this can go all the way from radio to gamma ray energies, with the gamma ray end has really, really tiny wavelengths and very high energy. And looking at the temperature associated with that energy, this is at the level of more than 10 million Kelvin, which tells you already this is non-thermal radiation because thermal equilibrium cannot be reached. Now, this little band of the colors are what the human eyes are sensitive to, but the actual electromagnetic waves extends to a much wider wavelengths coming from different processes and being a very powerful tool to probe the universe. But more recently, there have been more messengers from the universe. In addition to the nature of electromagnetic radiation, we have individual particles, what we call as cosmic rays. So these are neutrons, protons, and heavier nuclei that can carry a lot of energy as the matter. And usually the cosmic rays are the very high energy component of that matter. So they are the non-thermal distribution, and they are relativistic particles that are charged, interact a lot within a radiation field, and they also bend over in a magnetic field. There's also the neutrinos. So neutrinos are elementary particles. They're weakly interacting. They come with at least 3 flavors, and they are neutral. So which means unlike cosmic rays, they can travel for a really large distance without interaction, without changing their trajectory because they are insensitive to magnetic field. And finally, there are the gravitational waves, and these are also a new type of species, like messengers from the distant universe. So together they come as the multi-messenger astrophysics. So in this particular talk, I am going to focusing on the highest energy end of these messengers, and namely the gamma rays and neutrinos, as well as their parents, which are the cosmic rays, at the highest energy in the gamma ray and higher, in the gamma ray in the 10 to the 12 electron volts and higher energy. So in particular, this talk is going to be composed of 2 parts. First, I'm going to tell you a bit about the sky that we have seen with photons at the highest photon energy, namely hundreds of TeV or higher energy. And then in the second half, after telling you all about the wonderful stuff we see with gamma rays, we'll tell you a bit about the gamma ray obscured sky, a different view of the universe through the neutrinos. Starting with the first half. So a bit of the background introduction. A few slides ago, you might notice that this portion, once it's above ultraviolet, it's already not they are not penetrating the atmosphere. This is because they are being absorbed by the atoms in the atmosphere. That's why to detect these high energy gamma rays, the technique is is different from a direct observation. So either you go into the space, which is what the telescope below usually tend to so the x-axis here is in energy. In GeV, well, 1 GeV is 10 to the 9 electron volts. Y-axis is the flux or intensity of this emission. So up to about 1 TeV, 10 to the 3 GeV, the observation is mostly done through a satellite. So you go to the space, goes beyond the absorption starts by the atmosphere. There you can detect the photons using silicon photomultipliers carried in the module. And there we have seen this beautiful sky observed by the Fermi Large Area Telescope. There you can see that there is a bright galactic plane with many, many individual sources at the high altitude, which come from extragalactic emissions. And this emission has been dominated by either the active galactic nuclei or the star formation activities in the GeV to TeV energies. Now above 1 TeV here, it's starting to get really hard to be up to using a payload that because of the rareness of the events, as well as because that at higher energies, these photons did start to be attenuated by the background lights in the universe, like the cosmic microwave background. So it's getting harder to use a payload in space to detect them. That's why there are two major techniques to detecting these gamma rays on the ground. I mentioned there are absorptions. So these absorptions are exactly what was used to derive the initial injection into the Earth's atmosphere. So there's two techniques called imaging atmospheric Cherenkov telescopes, which is using imaging telescope to look for the air showers generated when the primary gamma ray hit on the Earth's atmosphere and generating a bunch of secondary cosmic rays and gamma rays and leptons. And those emissions are what we call as an air shower. So when we use imaging telescope to imaging those showers and use those shower structure to infer the initial primary photon. Another method is called air shower gamma detectors. So air shower gamma detectors, instead of looking at the time when the photon just arrived the Earth's atmosphere, it's looking at the time when the shower hits on the ground. So it's looking for the footprint of the primary gamma ray after going through the Earth's atmosphere using a fixed tank, a sample of water tanks. So the two techniques are sensitive in slightly different energy ranges. IACTs are good up to a few tens of TeV, whereas air shower gamma detectors are most sensitive at tens of TeV and above energies up to about PeV range. And the air shower gamma detectors are the technique that has been very popular and generating are producing a lot of interesting results at the highest energy lately. So two telescopes in the world are currently running with the most sensitive, the best sensitivities. One is called the HAWC, High Altitude Water Cherenkov Observatory, which is what this image is about. And this is a 0.1 to 100 TeV sky observed by HAWC. So now you can see that most of the sources are on a galactic plane. I switched the coordinate here. This is this dashed white curves indicating the plane, and you can see most of the sources are now galactic, a few extragalactic ones. And this is an image by the other air shower gamma detector called LASSO, which is a detector in China. And they have observed the sky with photons above 100 TeV, which they name as ultra high energy gamma ray sky. And you can see they're all galactic sources. And by the way, because these are ground-based detectors, they are partial sky. So right now, both detectors are only looking at the southern sky, and there's no such detector in the southern sky. That's why the southern sky is empty. Just to complete the story, the same technique of air shower detectors can also be used to look at photons at even higher energies at EeV 10 to the 8, 18 electron volts and higher. So far, no photons has been identified, and this is the limit set by the HAWC Observatory. Now, to bringing the whole picture just a little bit further away, the reason that people want to probe this TeV, PeV, and going higher and higher is because there is a very interesting regime in the cosmic ray spectrum. So this is a cosmic ray spectrum scaled with energy to the order of 2.7, with x-axis indicating the energy of the cosmic rays, which are the charged particles we have observed. This is plot based on decades of efforts from cosmic ray physicists, and there is a very prominent feature you see around 10 to the 15 electron volts, slightly higher than that, which is what we call as the knee, where you can see that the galactic cosmic ray spectrum bends over and started to turn it into a smooth transition of e to the -3 into some higher energy ranges. And then there is another change around 10 to the 18.5. That is what we call as the ankle. If you zoom into the knee region with modern techniques, with modern facilities, you have better and better sensitivities but basically what's showing here is the direct observation of the cosmic rays as well as indirect observation of the cosmic rays at the highest energy. That's why they have larger error bars. But nonetheless, you can see that this is the top one is proton, second line is the helium, but in both cases, you can see there is a turning around a few times 10 to the 16, a few times 10 to the 6 GeV, which is 1 PeV, where the spectrum cuts off. So that's why in the cosmic ray physics, people tend to believe that the galactic sources can accelerate particles all the way up to at least PeV energy. And therefore, it is a major task in the cosmic ray physics in looking for pevatrons, so PeV accelerators, particle accelerators. And specifically, we want a pevatron to satisfy the following condition, that it can accelerate protons at least to the energy range of PeV and with a spectrum that's harder than this range of roughly e to the -2.2 or e to the -2.4 power law spectrum. This is because the measured cosmic ray spectrum on the Earth has a spectrum of e to the -2.5, e to the -2.75, and that is after the diffusion of this cosmic ray in the interstellar medium, and that diffusion could further soften the initial injected spectrum. So to make the spectrum as observed, the initial injection, or where the cosmic ray from the source location, has to be as hard as e to the -2.2 to 2.4. And broadly, there's also literature referring to pevatron as any source, including leptonic sources that can make photons in the hundreds of TeV range. Now, a little bit more of information for the interactions. How do we connect these gamma rays and pevatrons? So the protons and hadronic cosmic rays can interact, and this interaction producing neutrinos and gamma rays through the decay of neutral or charged pions. But this decay products usually carries on average 10% of the proton energy for gamma rays and 5% of the proton energy for neutrinos. This is a distribution of the secondary particles, and you can see that this peak is around 10% for gamma rays. And therefore, in other words, if we want to look for these pevatrons that produces the knee in our cosmic ray spectrum inside the galaxy, we would need photons that can go all the way to hundreds of TeV at least, because these are the direct products of the PeV cosmic ray. And that is why it's such a big deal to look for these ultra high energy gamma rays, because they probe the pevatron directly. Now, the pevatrons has been a lot of efforts for the entire gamma ray astronomy in the past decade. This is an image of the pevatron in 2016. Basically, there was only one source back then. This was a source detected by the HAWC telescope, which is an imaging atmospheric Cherenkov telescope. They go all the way to 20, 30 TeV for the source and find there is a source, a diffuse emission coincident with this arc around the Sag-A star in our galactic center, and they conclude that diffuse emission is likely produced by star formation activities and through the proton acceleration and interacting with the gas in that region. Now, this is how it looked like this year, and it's even not a complete list. So we have a Cygnus cocoon, which is a similar structure like the galactic center Pevatron. It's a star formation region and producing gas. So it has a lot of gas in that region. And we also saw a supernova remnant at hundreds of TeV energies. We saw two very interesting jets of the black holes inside our own Milky Way, and these black holes have jets that go all the way to hundreds of parsec within our own Milky Way. So all these interesting sources are now very plausible candidates of these pevatrons that I mentioned earlier. So in the next few slides, I'm going to walk you through some of these sources, starting from the Cygnus cocoon. So this is a star formation region that has been known from observations of infrared as well as all sky surveys from different wavelengths. So this is a region and near the Cygnus X region, and it's in the heart, in the very center region of the Cygnus X region, and it composes of interesting the white stars indicating the interesting OB2 star clusters in the region. There are many active young stars like our own sun in those regions. And on top of that, there are presences of the heavy gas in the entire region. And the boundary, as you can see here, is clearly there's a clear boundary in this star formation region, which is regarded as a bubble that is inflated by the star winds of these OB2 stars. Now, in 2012, with the Fermi Lat data, a identification of a diffuse gamma emission is identified as shown here with the color indicating the significance of the gamma emission. But you can see that this gamma emission traces the infrared gamma emission pretty well and seems to mostly coming from spanning the entire region. And the conclusion from that Fermi Lat paper was by calculating the energy density inferred by the gamma emission, they concluded that this cosmic rays must be freshly accelerated inside this bubble. It cannot be some diffuse zombie cosmic rays that's staying for millions of years in the galaxy and interacting with gas in that region. That's not enough to explain the observation. So there was indeed freshly accelerated cosmic ray from this region. So this is a particle accelerator up to TeV energy. Then in 2021 with HAWC, we observed this region, another diffuse gamma emission, but now in the TeV range up to 100 TeV energy. And this gamma emission we see at hundreds of TeV also traces the infrared gamma emission. So the color here indicates the significance in the TeV gamma ray map, whereas the blue contours are the Fermi Lat, so it's this GeV contour. And as you can see, within uncertainties, they look very consistent and also similar to the structure in the infrared map. So apparently, gamma rays all the way from 0.1 GeV to hundreds of TeV trace the infrared emission. And this is a very likely scenario that the proton got accelerated either by certain sources inside the region or by stellar winds from the stellar clusters. And these diffuse protons inside the cocoon interact with the gas there and producing this diffuse gamma emission. And this emission, we propose that, as I just said, it can be gamma rays coming from proton acceleration by stellar winds, and we can either have a population of OB2 stars for staying there for millions of years and producing cosmic rays steadily, or it can be a recent burst from either individual sources or a supernova remnant and producing cosmic rays in a very recent episode. And that could explain this partial, this change of the spectrum So the red dots indicate the observation we see with Fermi-lab, and then the blue dots are the observation by HAWC, and you can see it bends over, softens the spectrum at a higher energy, which can be a feature of the cosmic ray diffusion of a recent burst. And this region is quite interesting. So we followed up with X-ray emissions with Swift XRT, which is a facility with very low brightness background. And we ended up finding no significant emission from this spots inside and outside the cocoon. And that placed one of the tightest constraint on the X-ray emission from the Cygnus cocoon, and therefore constrain the models by relativistic electrons in a ISM type of magnetic field. They are expected to producing a synchrotron radiation, and that's not seen. So that provide a very tight constraint to the flux of the gamma ray that may be made by electrons. And this again back up the idea that this could be a proton source and therefore a pavotron. This source was also observed by LASSO up to now 3.7 PeV gamma ray energy. So it's indeed a very intriguing star formation region with plausible pavotrons. Now the next is about supernova remnant. So supernova remnant has long been proposed as cosmic resources in the galaxy, but at the very high energy, hundreds of TeV energy, we rarely see a supernova remnant. And in fact, this is the only one that we are seeing in above hundreds of TeV. So this is a supernova remnant that is at a distance of 800 parsec, very close. And it's roughly at the age of 10 kiloyear, middle-aged, relatively young middle-aged. It was seen in the radio band already in 2001, and this whole region is polarized. And this big fat body is called as the supernova remnant, and that very dark dot is where the pulsar locates. And the structure is believed that the pulsar and the supernova remnant are co-formed, but the supernova remnant is expanding in a direction that the density is relatively low, so that's why it formed this head and tail shape. Tibet AS Gamma Observatory, which is another air shower gamma detector, even before HAWC and LASSO, that they identified a point-like emission from the tail of the supernova remnant in 2021. And that location of the gamma emission is co-located with a blob of molecular cloud, making them conclude that this is likely a region of proton-proton interaction. But on the other hand, looking at the X-ray emission, there is a diffuse X-ray emission seen from both the head and the tail of the supernova remnant, and that emission is consistent with a non-thermal synchrotron radiation by electrons in the entire region. So the picture is a little murky, that it seems to be a plausible PeV supernova remnant, PeV cosmic ray supernova remnant, but on the other hand, it's likely that this gamma emission that's being seen can also be produced by electrons. So that's why we looked into the Fermi-lab data and find some very strange behavior of this supernova remnant. Namely, that if you look at the data in a range of 10 GeV and above, there is indeed a gamma emission at the tail region of the supernova remnant with a location very similar to what TeV gamma ray observatories have observed. But when you look at below GeV, so between 1 and 10 GeV on the left-hand side, this guy seems to be muted. There is no emission from the body. And we dig into the data very hard, checking all kinds of systematics. We use the phased data so that the pulsar, which is extremely bright in the GeV band, is not polluting the data. We're only choosing the data when the pulsar is away from us. And doing all kinds of technical checks ended up make us concluding that this is a real absence of emission and a very tight constraint on the flux in that energy range. And therefore, this tight constraint make it a very interesting coherent picture that if the electrons are making this hundreds of TeV gamma emission that the air shower gamma detectors are seeing, then the brainstorm emission of these electrons would be at this range where we should see a signal. The absence of such a signal indicating that this TeV gamma emission has to come from something other than electron. And in this case, this analysis and this constraint specifically support a model with proton contribution and more than 5 sigma significance, and making this a first Pevatron supernova remnant candidate. And this supernova remnant candidate is very interesting because it doesn't look at all like the Pevatron supernova remnant people have been looking for over the years, namely with a pi and decay signature at GeV, at the rest mass of the proton, and extending all the way to PeV range. But instead, this guy has a very hard spectrum, of a spectrum almost harder than e to the -2, and go all the way to PeV energies for the proton injection. So it could be one of the first of an iceberg of this population of a supernova remnant that could be Pevatron accelerator. And finally, I'm really excited about these jets, these mini black holes with very large scale jet in the Milky Way. Starting from SS433. So this is a microquasar that has been well studied in lower energies. And in particular, this image we put together shows a W50, which is a nebula in a radial band, as well as a set of large-scale jets in different colors, combining different X-ray energies. And this large-scale jet is passing through this initially rounded supernova remnant and forming a kind of a head and a tail of a fish-like shape. And these are a set of large-scale jets that has been seen in X-rays. Now, with 2 years of HAWC data, we already find very interesting gamma emission from these jets. Now, this point, like TeV gamma emissions are seen indicated by these colors. So even though I have been looking at this many, many times, it's still amazing for me to think about it when you look at this image, that this gamma emission, which we see from these jets, are not coming from the black hole. They are not coming from the end of the jet where the jet is interacting with the ISM, forming termination shocks. It ended up coming from somewhere inside the jet. So this is the first time where a set of astrophysical jets are resolved at such high energy. And the location of the emission is very informative because this suggests that the acceleration of these electrons must be inside the jet and at the location about 30 parsec away from the compact object. Now, noting that we are talking about tens of TeV gamma emission, therefore electrons and energy of hundreds of TeV. So these electrons are pretty short-lived, so they cannot travel from the hole to this emission region. It has to be on-site radiation and on-site acceleration. And that's why we concluded that this acceleration site for these electrons must be inside these jets. And putting the multi-wavelength observation of those gamma emitting sites together, radio XM Newton, gamma ray, GeV, and TeV observations, we concluded that this GeV to TeV gamma emission may be explained by inverse Compton radiation by relativistic electrons that cools very efficiently. And this is not a hadronic Pevatron, but does show that the jets may accelerating hundreds of TeV electrons. And this observation was followed up by the HAWC telescope, and they identified the same set of the jets. They even identified a gamma emission sites that vary slightly in different energy bands, and this explained as the shock velocity changes along the jet size, along the jet axis. We also have new data with HAWC in 2024. We have more data and refined energy spectrum, and some interesting emergent new fact is that both HAWC and HAWC data is suggesting a deviation from the single zone leptonic models. So either additional component comes in at a higher energy from either protons or other or a multi-zone model would be needed, even for one of the nearest sources. This is also suggested by the observation of HAWC Observatory, which identify on top of the two jets another emission near the compact object. Another jet that I think is really interesting is, and also surprising for us, was the source V4641 Sagittarius. This is a source that's really surprising that we couldn't believe our observation for a long time. So here is what it's like. So this is an observation. This is an X-ray binary with a 3 to 10 solar mass black hole. It previously was seen in radio and an X-ray as a mini blazar, meaning that they have super Eddington flares and they are beaming, they are going almost, they're just almost inclined and going toward the observer. Now, with the HAWC data, we find a set of point-like sources next to the source. So this plus is the X-ray binary, and the color indicates the significance in our data above 1 TeV. There are individual sources nearby, and these sources, none of them appear to be associated with the gamma emission, except the 4641 SGR, this X-ray binary. This source has happened to be below the galactic plane and in a very empty region. So it's very hard to look for the associate. It's a pretty empty region. So there's no other source other than the V4641 SGR source that can be possibly associated. But this source itself has no extended jet seen in X-ray or radio or in any wavelengths like SS433. And that's why we couldn't believe it at the beginning that this X-ray binary is producing something that large. And then when we look at above 100 TeV, where we have a better point spread function, and you still see that peanut-shaped emission out there with the plus indicating the compact object roughly at the center. So this elongated emission is possibly connected to a set of jets. If we think the SS433 jets are powered by the central jet and do a similar compute calculation, assuming a similar age of these microquasars, you would end up getting a large-scale jet of hundreds of parsec. So we suspect that could be the case. And later on, when we look into the emission, the spectral shape, as well as flux of this two point-like source, they ended up to be very similar to each other. So I think I have it here, right? So this image here shows the flux as a function of the gamma ray energy, and the gray color indicates a fit to the two source as one. So if I fit this whole region of the peanut with as one source, you would obtain this total flux. And if you fit two individual point-like sources, which as resolved by HAWC, our data suggests that it's more consistent with two point-like source at that peanut location, north and south peanuts, and their fluxes as well as spectra look almost identical, despite being more than 100 parsec away physically. So that made us believe this could be a set of jets here, a large-scale jets, and this add to SS433 as the second galactic microquasar that have a set of large-scale jets. And the gamma ray emission from the source itself is also very interesting. It's e to the minus 2.2 all the way to hundreds of TeVs, among the hardest source ever seen by air shower gamma ray detectors. And we cannot really differentiate the proton or leptonic scenario here without the lower energy counterparts. That's why a campaign, a multi-wavelength campaign, has been carried out for this source, and efforts are still going on. So these are a quick summary of the first part of my talk. I have to skip many interesting sources due to the interest of the time, but the reason of showing up this image is to give you a sense of the pevatrons or hundreds of TeV ultra high energy gamma ray sources we have seen so far. And you can see that there are multiple source classes being evolved. It's not dominated by one species. It's like many different type of species. It's like a zoo of pevatrons. So I'll stop here briefly since this is a remote talk in case there are questions. Okay, if not, I'll move on then. Okay, so after telling you all about this beasts in the gamma ray sky, I'm now going to tell you there is yet another whole population that we have not seen with gamma rays, and that's because these sources are likely gamma ray obscured, and you cannot see them with electromagnetic waves, or it's hard to see them with electromagnetic waves, and you need neutrinos to see them. So the neutrinos are weakly interacting particles, as I introduced earlier, and due to their weakly interacting nature, it's very hard to detect them. That is why it has been decades of effort, all the way from Amanda to IceCube, and now to a lot more neutrino detectors being built internationally in the world to detect these neutrinos. But so far, a lot of progress has been made. The first neutrinos has been observed, and here are a few fun facts about these neutrino and their sources. So first of all, these neutrinos do exist. This meaning these high energy cosmic neutrinos. So here is a plot showing you the amount of the events as a function of reconstructed energy in the detector based on IceCube observations. And the red dots are the data. And these neutrino emission can be composed of various components. Either they come from the atmospheric background where the cosmic rays interacting with the atmosphere producing secondary neutrinos. They can also come from real astrophysical neutrinos. So here you can see that this astrophysical neutrinos stands out of the atmospheric neutrino conventional background significantly, and therefore the data is mostly likely explained by the astrophysical neutrino data all the way to from tens of TeV all the way to the highest energy. So a diffuse flux of this astrophysical neutrino has been detected by IceCube. Now, the next interesting fact is people tend to think it's so hard to detect them, therefore they must be rare. It's actually not true. The flux that has been detected so far instead suggests there are a huge population of neutrino sources and they carry a lot of energy. Just to give you a sense, this is a plot showing you the optical power carried by optical transients as a function of the maximum energy that a proton may be accelerated by the shocks of these transients. There are different populations, core collapse supernovae, tidal disruption events, FBOT, fast bright optical transients, superluminous supernovae, and smaller version of them, novae, but more popular version of them. But the point here is, even when you sum up all the available powers, all the available shock powers by the optical transients, you are still far away from explaining the IceCube diffuse neutrinos unless the shock acceleration efficiency by converting the shock power to the relativistic proton energy is 100% efficient, which is unrealistic. That's why, so in other words, the transients powered by non-relativistic shocks can barely explain the diffuse neutrinos. And the neutrino fluxes that has been observed by IceCube has to come from more powerful sources or more long-term emitters like jets of AGNs. And another surprising fact about these neutrino sources is that they could be gamma opaque. So this is a complicated plot. Let me walk you through it. So these data points are IceCube measurement of the diffuse neutrinos. There are different event selections. That's why there are different data sets, but they all point to a consistent flux at the level of 10 to the minus 7 GeV per centimeter square per second per steradian at tens of TeV energies. Now, this neutrino can come at their own as weakly interacting particles, but the processes that produce the neutrinos would also lead to the production of gamma rays. And this gamma ray emission, this individual gamma rays would cascade down in the intergalactic medium and producing secondary gamma rays going all the way down to GeV energies. And this is described by these orange colors with different line styles corresponding to different assumptions of the initial neutrino spectrum. So if the sources themselves that produces the neutrinos are gamma ray transparent. Namely, that the gamma rays co-produced with the neutrino would just leak out of the source and do their travel all the way from the source to the Earth. Then these gamma rays would producing cascade signals. Namely, they are going to interact with a background radiation field like the CMB photon, producing secondary electrons, and those electrons would synchrotron radiate in the magnetic field, as well as producing its own pair production, producing additional gamma rays, and that gamma ray would again hit another background photon, producing electrons. So this chain of interactions would continue on until that the last generation of photons are no longer is below the threshold of the pair production. So assuming that electromagnetic cascades continue on to from these populations of neutrino sources, then we would end up seeing a gamma ray flux that can be as high as the entire diffuse gamma ray flux that has been seen by Fermi-Lab. So that tension between the gamma ray data as well as the prediction of the gamma ray cascades from neutrino sources suggests that the sources itself could already have the attenuation of the gamma rays so that the gamma ray do not come out straight. And attenuation of these gamma rays, meaning that the sources could be obscured to these gamma rays. And this gamma ray energy doesn't go away. These are photon energy that will continue to go down to lower energy, absorbed and passed down to the lower energy. And these attenuated gamma rays may show up at lower energies. So in this plot, I'm showing you a few cases. Again, the gray colors indicating neutrino models and orange color indicating the corresponding gamma ray fluxes. This time assuming that their sources attenuate these gamma rays at the first place, and therefore the cascades already happened inside the source. And the cascaded photons would eventually leak out from the source because they no longer interact and they are stable based on for the interaction of the extragalactic gamma ray background, and they can leak out and go out to the lower energy. And in such a scenario, the MEEV gamma ray background can be tightly correlated with the neutrino sky, which is an interesting scenario that would suggesting that the neutrino sources might show up instead of GeV gamma ray sky, but at the MEEV to sub-GeV sky. And this is also hinted by individual source observations. So NGC 1068 is a Seyfert galaxy and one of the first candidate neutrino sources at the based on a search using the Northern Track data. 1068 was the region with the highest significance and a 4.2 sigma post-trial significance, so an indication of the first neutrino source. But this source has a flux that is very high again, comparing to the gamma ray data. So the green color here indicating the gamma ray flux observation observed by Fermi-Lab as well as upper limit observed by MAGIC. And the neutrino flux is indicated by the blue band. As you can see that the neutrino flux is orders of magnitude higher than the gamma ray flux. And this is amazing as you think about it, because we have been using photons to look at the universe and we see all these interesting sources. But now when you switch to the lens of neutrinos, you started to see tens or hundreds times of energy that was not known before. And this is truly a new window of observing the universe. So with this particular case, and similarly, there are several other 3 sigma level sources that shows very similar features, that the neutrino flux is significantly higher than the gamma ray flux, suggesting that the source is gamma ray obscured. And finally, some of these neutrinos that have been detected turn out to be galactic. So this neutrino emission has been observed finally after more than 10 years of operation of HAWC Telescope. We ended up seeing this neutrino emission from the galactic plane, and this emission can either come from the diffuse cosmic rays interacting with the ISM gas, or coming from individual sources that are unresolved in the neutrino data. But either way, these are galactic neutrino emission finally seen. Now, this galactic neutrinos is also indicating interesting facts about the sources. So here are the universe, the full sky map observed in photons by Planck at radio band, Eero-Theta by X-ray in the X-ray band, as well as Fermilab you see earlier in the GeV band. In all of the cases, you see this very bright band at the very center, which is our own galactic plane, plus diffuse emission in the background. Now look at the last panel, which is the IceCube neutrino sky map for the full sky. And do you see a galactic plane? Well, you see a little bit of it. These are consistent with the molecular clouds in the galactic central region and the plane galactic diffuse emission structures. But other than that, it's not as striking as in a electromagnetic wavelengths that you can see this galactic plane. And this is because of a simple reason. Because if this is simply suggesting that our own galaxy has not hosted the type of the sources that dominate the isotropic neutrino sky, at least in the past tens of kiloyears. Because had we also having such a extragalactic neutrino engine, by geometry, our own galactic plane should shine out of the diffuse background, like in electromagnetic waves. But the fact that in the neutrino sky, the diffuse background, the extragalactic sky is brighter, is suggesting that we really don't have a bright source locally. And we did calculations, including all kinds of uncertainties of neutrino emission models in different galaxies. And we concluded that even combining all kinds of uncertainties, the neutrino luminosity of the Milky Way is orders of magnitude lower than the average neutrino luminosity of an external galaxy. And this could, in principle, be related to the inactivity of the supermassive black hole in our own galaxy in the past kilos of years. So these sources are, I've now shown you a list of features that we have known about the neutrino sources. And we still have no idea what they are, at least for the majority of the neutrinos that has been detected. But yet this gives you some features, some ideas about what this monster would look like. And as you can see again, they look very different from what you might expect of the sources in the gamma ray sky. So going back to this gamma ray opaque sources, there has been models suggesting how to explaining this gamma ray opacity. So this source itself has it's a Seyfert-2 galaxy. So this is the image showing the source there. There is a very bright core and plus active star formation activities in the entire disk and the galaxy. And zooming into the core region, you see there are individual hotspots in the ALMA band, and these hotspots are interpreted as individual jets, as jets interacting with the nearby gas and bending over the jet direction and producing the spots where the jet hit the pre-existing material, producing these bright knots. And in the very, very center is not resolved, but believed to have a supermassive black hole and a bright corona, and also a small radio jet. So based on these regions, model has been suggesting that the emission of neutrino can happen either in the corona region, which very close with tens of RG distances from the hole, and there either stochastic acceleration or magnetic reconnection can push particles to the PeV energy ranges, and then the bright radiation from the disk would interact with the proton, producing photon-pion interaction, producing the neutrinos. Or other native models suggesting that these hot knots, where the jets hitting very dense ISM gas in those regions, can also producing neutrinos, although not as high as what IceCube has seen. But the bottom line here is the neutrino production could, in principle, come from very compact regions, and these regions need to have very strong radiation field. That's why the gamma rays coming together with the neutrinos would be attenuated. And if these sources turn out to be the actual neutrino sources, then high-energy neutrinos would provide information from the sites that would be challenging for astronomy because these are locations that's very, very close to the hole. And finally, just a quick touch of the galactic neutrinos as well as the corona neutrino scenario. As you know that despite the fact that the supermassive black hole and the stellar mass black holes are really different in physical sizes, they share very similar compactness. And these compactness parameters are the key to both interaction and acceleration. So we applied the same the corona model that works for extragalactic neutrino sources to our own mini black holes inside the Milky Way. And this suggests that we can obtain a similar conclusion of the neutrino production, which is consistent with the non-detection. But in general, if we can, in this particular case of Cygnus X1, when assuming that the hard state is when the corona region is dominating the entire disk region up to tens of or hundreds of RG, whereas the soft state, the corona is much shrinked and smaller with a larger radiation background from the disk, then we can obtain interesting models that may explain the GeV gamma emission as well as neutrino flux. And interestingly, going back to my gamma ray first part, the model predict a gamma ray emission that happens to be detected consistent with the detection by the LASSO for one of the Cygnus X1 microquasar. So that is hits the conclusion of the talk, which hopefully gives you an idea of the recent gamma ray observation, which we have started to see very new looks of individual sources in the Milky Way. And there are good candidates of this pevatrons, which could contribute to the cosmic ray knee. But on the other hand, it's still very challenging to identify the nature of these accelerators using gamma ray only. That's why the neutrinos comes into play. But neutrino sources themselves are very mysterious at the moment, that we have seen them both from our own galactic plane and extragalactic sky, but the specific neutrino sources is still in question. But we do know at least that our own Milky Way does not have the type of the powerful accelerator that produces the bulk of the cosmic neutrinos. So the question still remains out there for the next generation detector or for the series to understand what exactly can make these neutrinos. Okay, thank you.
Thank you, Ke. That was really exciting results. Since I'm not in the room, I'm assuming someone can give the microphone to someone who's asking questions.
Yes, I do have the microphones.
Awesome, thank you.
Anyone
I also
have
see
any
questions on
questions?
Zoom. Shall I do that first?
Yeah, let's do the Zoom question first.
From Boris Braverman, why are all of the 100 TeV sources we can see localized in such a small fraction of the sky?
Oh, it's because limited by the sensitivity. So okay, let me explain the question. Let me show one of the image here. And so if you're asking why the TeV gamma emission are so condensed in a small fraction of the sky, the reason is because that this emission is absorbed. So the TeV gamma rays and higher energy gamma rays are absorbed by the extragalactic background light. The horizon of 100 TeV gamma rays is at the level of tens of kiloparsec. So basically they are local. Any further distances, they would be attenuated by the pump pair production. So they would interact with the CMB photon in general. And that's why we are mostly at this high energy. We are mostly seeing our own galactic plane plus a few nearby sources, extragalactic sources. But then if you're asking that the physical distance of most of these sources are at a few kiloparsec, not much further than that. This is because it's still sensitivity limited, that the gamma ray flux from these sources we can see is pretty limited by the sensitivity of the current generation detectors. That's why we're mostly seeing the bright gamma ray sources in the nearby distances of the Milky Way.
Right. Any questions in the room?
Hi, thank you for the talk. So I think you explained this, but I missed it a little bit. Could you please briefly explain again? How do we know that certain particle is freshly accelerated in some pevotron versus it, already having a high energy particle coming in and just scattering off?
That's actually a very good question. The short answer is case by case, and in many cases we do not know. So one good case is this Cygnus cocoon region. So this region is a region that's well measured in multi-wavelengths. So there is a good understanding about, for example, the gas density or at least column density in these regions. And the emission that we see in gamma ray from GeV to TeV energies has an energy density way higher than the energy density of a cosmic ray that has been sitting there for millions of times. So there are freshly accelerated cosmic rays by the sources out there. There are also cosmic rays that are what we call as cosmic ray C. So these are particles that have been injected by individual sources in the Milky Way millions of years ago, and then they have been traveling as a zombie in the galactic magnetic field ever since. So these are a good population of cosmic rays in the Milky Way, and they are the dominant emitter of the diffuse emission that we have seen. But if you compare the cosmic ray density needed to producing the gamma ray emission to the cosmic ray density of those diffuse emission, then you can conclude that there's no way that those zombie cosmic rays can make such an emission. So that is why we are pretty confident that these emissions we see in gamma ray are coming from sources inside the source. I mean, from individual accelerators, either the winds, stellar winds, or certain specific microquasars like Cygnus X-ray is in this region. There's also one candidate supernova remnant and a pulsar wave nebulae in this region. So there are individual interesting sources that could be bursting cosmic rays into this bubble. Or there could be a stellar wind. There are many OB2 stars, so the stellar winds can also make cosmic ray acceleration. But this has to be something inside this region. It cannot be from somewhere else. Otherwise, the energy density would be different.
Thank you.
Right. Any other questions in the room?
I can ask another question. Sure. Okay. So another question is, so what would make you, so you're saying in like this particular source that you see, it is it's easy for you to figure, well, relatively easy for you to figure out which things are like fresh particles, because you can compare against some background, and then you can figure out that the background can't do something like this, so this has to be produced. So why is this particular source easier to do that kind of procedure with, and why would, on some other source that you look at, that would not be so obvious to like just apply the same methodology and figure that out?
Sure. So, for example, there are a few recent detections by the HAWC Observatory, and they call as dark sources. So, by dark sources, they mean there are no counterpart in lower energy gamma ray, or in some cases in the entire catalog of galactic sources in different wavelengths. So, and in such a case, the dark source, the gamma emission can either come from a source that somehow has not been resolved in a multi-wavelength observation. Then in that case, it would be a local source like this one, but somehow that source has not been seen. Or it can be a case where the cosmic rays are produced elsewhere, nearby, for example, and those cosmic rays hit a molecular cloud that happen to be in that region and then producing this gamma ray. So that would be like escaped cosmic ray from a nearby source or from even a distant location to producing the gamma ray. So this new observation of these dark sources make this scenario of a remote source and a different location of the acceleration and interaction possible. So that's a observational fact of the alternative scenario.
All right. I guess there are no more questions in the room.
So one more online from David Bailey. Do neutrino and gamma ray, I assume, production and absorption processes make it natural that neutrino and gamma emission of a source should be anti-correlated?
Oh, this is an interesting question. So if you look at NGC 1068, one of the first neutrino sources, okay, so that's the one that people have been thinking about a lot lately. So in this case, the way that this source was identified in data is using gamma ray catalogs. And the gamma ray catalogs, so the source itself also emits gamma ray. So it's not necessarily anti-correlated because even though the gamma ray flux is 2 orders of magnitude lower than the neutrino flux, the gamma rays are still produced. And these gamma rays in particular are likely coming from the star-forming activities of this galaxy, whereas neutrinos can come from a much compact region inside the core of the AGN. So because of the complication that gamma ray can be produced by different sites, and not necessarily only by the neutrino emission side and getting obscured, that complicates the way of thinking them simply being anti-correlated.
For people interested in how that works, come talk to me. This is one of the things I'm trying to model with plasma physics, and I'm working on with Ke in our Simon's collaboration, for example. Online, there are no more questions, and in the room, neither. I had one, if I can.
Of course.
Ke, do you have the hope? It's maybe more philosophical question, to see gravitational waves together with neutrinos and electromagnetic signal, so that we have 3 windows?
Yeah, there is this model that I worked with Brian Metzger a while ago on the neutrino production from a long-term pulsar remnant, magnetar remnant from a neutron star merger. So of course it relies on multiple strong assumptions, namely that a long-term magnetar can be formed after the neutron star merger, and such a magnetar had ordered magnetic field so that a very high potential may be provided by the magnetosphere, and particles, protons specifically, may tap those potentials and go all the way to ultra high energy in cosmic ray energies. But if those series of assumption applies, then one could indeed expect a scenario where a set of neutron star collapse, form gravitational waves. Then days after, you started to see high energy neutrino coming out of the merger remnant. And in that particular case, the neutrinos would be a very clean signal comparing to electromagnetic counterparts, for example, which may come from different aspects of the magnetar. But neutrinos would be a very clean signal of indicating the formation of magnetosphere and a very strong potential provided by the electromagnetic energy going outwards, because the neutrino would go out without much interaction. They're weakly interacting particle even at such high energy, but the spectral shape and also the delay of a few days would give you the information about the density of the region as well as the location, for example, the distances of the acceleration sites.
Well, thanks again for this talk and for answering our questions, and for making the time. I hope your 1-year-old is feeling better.
Yeah. Thank you so much. And really sorry for not being able to go there. I wished to see you all guys, but hopefully another time.
Definitely.